So, Category 1 review. Category 1 is all about properties and attributes of functions. A total of 8 questions are going to come out of this category, which doesn't seem like very many, but there's a lot in here, so we're going to go through step by step. Alright, supporting standards, I want to begin there, and that was just what we began with at the beginning of this year. Notice the verbs they underline here, that is the action that you're required to take here. So you have to be able to identify and sketch graphs of all of the parent functions. This is a supporting standard. It's not going to be as heavily tested. But if you don't know your parent functions, then you're obviously not going to know how to do the transformations or any of the other things. So what I'm going to suggest here, we'll go through and describe each one, but I suggest you make some flashcards and just draw the pictures, put the name on them and the equation, because you need to know what they look like, what they're called, and what their parent equation is. So linear function is f of x is equal to x. It's increasing from left to right, has a positive slope, it's going to go through the point 0, 0. The slope is 1 over 1. Quadratic function is f of x equals x squared. So this is our parabola. It's going to open upward. A value is 1, and the vertex hk is going through the origin, so h and k are both 0 here. Okay, this is not going to do this again. Absolute value function, we didn't use this one as much, but it also opens upward just like the quadratic function. Its vertex is the point where it turns here, is at the origin, so its h and k are 0, its a value is 1. Square root function, we still call this a vertex where it starts right here, and a value here is also 1, h and k are 0, and this is opening towards the right, so this is a part of one of the horizontal parabolas that we've been looking at recently. Okay, exponential function can be seen in a lot of ways. Wait, I want to go back for a second. Absolute value function, I just want to remind you on your calculators, because I still see people getting confused on this. When you graph this, there's a line on here somewhere that people keep trying to use, like a straight line. I don't see it right now. Anyways, the key you want to use is this one right here that has the picture of the absolute value bars in it, and then you want the absolute value here to graph that. So make sure you use the right key on your calculator. Okay. Exponential, this is my growth function, and most people consider the parent function to be 2 raised to the x power. And so that's going to go through the point 0, 1 right here, and it's going to be increasing from left to right. And there is also the parent decay function, and that is generally considered to be f of x equals 1/2 to the x power, and that's going to be coming down exactly opposite this and also go through the point 0, 1. So you could see both the growth parent and the decay parent, but this is the one that you're going to compare any transformations to right here. So then if I consider this the exponential parent function, then the logarithmic parent function, which is the inverse of that, would have the same base. So a log of base 2 of x. And you could also see this as just log of x. But it's going to go through the point 1, 0, because these are inverses, which we'll talk about in a minute. And then finally our rational function. And this is the one I think people have most trouble remembering. And the way I help remember this one is rational sounds a lot like fraction, and its equation is a fraction, and its graph is broken into 2 parts, just like this equation is broken into 2 parts here. And if we think about the line right here, so if it has this line breaking it apart here, that's your asymptote. You could also write a fraction as a decimal with a point, and so sometimes we have undefined points in our rational functions too, and we'll look at that more later when we get into rational functions. Second supporting standard is about inverses. So describe and analyze the relationship between a function and its inverse. So the steps we use here when we're finding an inverse algebraically is you're going to switch your x and y variables and you're going to solve for y. Notation you need to know because they may not say in this find the inverse. They might just give you this notation, this f negative 1 of x, which means inverse. So it's very important that you have this down right here. Let's look at some examples. So important things to know. Inverse of a function will undo the original, basically. And so it's your x and y changing places. So you can tell by the table. So if I have original table here, just my x and y values are going to switch. So we can always just build a table. Like if I had this graph given to me right here, I could just go along here and find some points and mark them. Okay, it's red. No, it won't show up. So I could just come along right here and find points that go through corners. Like I can find a point right here. That one's pretty good right there. Right here. And right here. Anything that's going right through a corner point, and I mark those points. And then build a table. So just make a table like the one right here. And then switch those around and plot my new points. And so I can create an inverse that way. I can check the points on this one as well and see if they are opposite of this table. So just based on the graphs and tables, I can find most of my inverses. But when I can't, I need to do it algebraically. We can find inverses of just points. So the inverse of this, I lost my pen. Would be the set of, and so everything's just going to switch. So I have 4, 3. That didn't write very well. And I'm using a tablet, not my smartboard, so I apologize. This is messy. Negative 2, 1. Negative 1, 5. And 2, 0 would be my inverse. And then they also ask, is your inverse a function? So then I just look to see if my x values repeat. And I have negative 2, negative 1, 2, and 4 don't repeat, so this is a function also. Okay, find the inverse for these functions. So I have a linear function here. The inverse of a linear function will be another linear function. So first of all, I need to remember that f of x, or g of x, or h of x, or whatever else I'm looking at is y equals, so this is really y is equal to 1/2 x plus 3. So step 1 says I'm going to switch my x and y values. So I've got x equals 1/2 y plus 3. And then I'm solving for y, so I'm working PEMDAS backwards. The first thing I want to do is any addition or subtraction. So I have addition right here. I'm going to subtract 3 from both sides, which gives me x minus 3 over here equals to 1/2 y, and my 3 will cancel here. And then the opposite of dividing by 2 is multiplying by 2. So I'm going to multiply by 2 here, which is going to cancel here so that I have 1y. And then I can distribute here, so I get 2x minus 6 is equal to y. And so the inverse, the inverse of this, f negative 1x, would be 2x minus 6. And then we can also check that on our calculator. So let's go to our calculators. And we're going to graph 1/2 x plus 3. And we're going to graph 2x minus 6. And so we should be getting a reflection of these two graphs here across the y equals x line. So we can check that by just graphing the y equals x line. That's our reflection line here. And we can see that the same thing is happening on this side of the line as is happening on this side of the line here. So those are inverses of each other. And when we have a quadratic function here, we're going to do the same thing. We're going to find the inverse here. So this is actually y is equal to x plus 6 squared. I'm going to run short on room here. Plus 2. And so I'm going to come over here where I have more room. So that is, I'm going to change my variables. So x equals y plus 6 squared plus 2. So I'm solving, so I'm working backwards. Addition, subtraction first. My parentheses are going to be the last thing I do. So I'm subtracting 2 from both sides, which gives me x minus 2 is equal to y plus 6 squared. And then before I can do anything in here, I have to undo this because it's in parentheses. So that means I have to take the square root of both sides. So over here I get the square root of x minus 2. When I take the square root here, it's going to cancel that squared. So I'm going to have just y plus 6. Now I can move that 6 over. Remembering that this 6 is not under a root like this negative 2 is. So got x minus 2 under the root. And then when I subtract the 6, that needs to go outside of the root. Okay, so we run into one problem here. So let's look at, we've got x plus 6 squared plus 2 in our calculator. X plus 6 squared, yeah. So here's my graph right here. Now the thing is, with an inverse, it's reflecting over this line, but it has to be a function. So if I reflected this over the line, what I would get would be, no, I want to write this. It's not going to let me write. Alright, it's not going to let me draw that there. But what I would get would be a parabola on it, a horizontal parabola here, and so that's not a function, and so we're going to have to restrict this somehow. So we're going to restrict it based on the vertex point here, and my vertex is at negative 6, 2. So my h value, my domain, I'm going to restrict my domain to everything only greater than or equal to negative 6. So I'm basically ignoring this side of the graph here. So let's kind of draw a picture of that. And so I have this parabola here, and its vertex is right here. It's negative 6, 2. Alright, so if I'm creating the inverse of that, if I leave it just like it is, and I'm looking at the inverse, I have the positive side of the square root and I have the negative side of the square root, and that's not a function there, so that's not going to work for me. So what we're going to do then is not use that, and we're going to say, okay, this is true, this is my inverse only for values greater than or equal to negative 6. So I'm going to restrict this. So when I write out this inverse, I'm going to write it like this. So I've got f negative 1 of x, or sorry, this is g, not f, because that's what they gave us. Okay, so I have g, negative 1 of x. The inverse is equal to the square root of x minus 2 minus 6 only when x is greater than or equal to 6. So what I'm saying is I'm only going to take this portion of my graph right here and look at it, because if I draw just that, I'm going to get a graph that looks like this when I flip it, and that's a function. So I'm restricting my domain, and we saw a question like this on the last district test. In fact, a couple questions were related to this. And so they were looking for, do you understand that if I flip this whole thing onto its side, it's no longer a function, and so I can't call it an inverse function because it's not. And so we've restricted it to only that part right there. So if you find your vertex point right here, you're restricting it to everything greater than your x value when you do the inverse. The other thing you might see with inverses is here, verify that f and g are inverses. So one thing, probably the easiest, fastest, because this is about speed, thing to do is graph this, and then graph your x line through them and see if it divides them in half. If you can't tell for sure, make a table for this one, make a table for this one, see if your x and y values are switched. If you don't like that method, pick one of them. So say we pick 2x plus 14, do the same thing as you did up here and see if you get this as the inverse. So if you get this, then yes, they're inverses. If you don't, then no, they're not. Okay, so I'm going to give some problems for you to try on your own. So at this point, if you want to stop and work problems and write them down, you can just pause the video and do that. I'm going to move on from there. Readiness standards. Transformations are going to show up in every category, because not only are they in your category 1, but then for each function that we went in and studied, that's one of your standards again. So I expect there to be quite a lot of transformations on here. So all I'm going to say in this category review is just know what A, H, and K do. A stretches when it's greater than 1 or less than -1, compresses when it's between 1 and -1, and it reflects across the x-axis when the number is negative. And so you need to remember that stretching generally means your graph is getting narrower, compressing means it's getting wider, just like when you stretch a rubber band or you compress it. Your H, I'm not sure why people have trouble with this. H is just like horizontal, so it's moving left and right, but you have to remember that H always goes the opposite direction of the sign because the formula has a negative in it already. And then your K is going to move it vertically whatever way it says. If it's positive, it's going up. If it's negative, it's going down. So anytime we talk about parameter changes here, your original is the parent function. So if you don't know your parent functions, then you don't know what to compare the question to, because you're always comparing back to that original parent function, which is why that's a supporting, but it's necessary. The other readiness standards, there's two others. One is to be able to collect and organize data, make and interpret scatter plots, fit the graph of the function to the data, interpret the results, model, predict, and make decisions. So there's not a lot I can say here. I've tried to include in the review sheets a couple things where you were doing some scatter plots and then making predictions based on things, but basically this, you all know this stuff. You need to be able to represent a problem using an equation. You need to be able to write or understand a description of the problem. You need to be able to create a table of points for it. You need to take those points and plot them and create a graph, and then recognize from the graph what parent function it represents based on the shape. So this is your quick graph right here. When you do your tables, you're looking at quick graphs first, because we don't want to do a regression on a linear regression on something that was actually quadratic or exponential. And then if no other information is given, just to draw pictures of things, because that makes them easier to understand. And then the other big one that comes in, again, every category, so every function we talk about is domain and range. So I'm not going to do a lot of examples, but I did include a lot of examples in the practice sheets. One I wanted to talk about is we had something kind of similar to this on the last district test also. The one on that test went off with an arrow right here instead of stopping. And so the one that was on that, it did something like, did something like this. It had a closed circle here, had an open circle here, and then it went off like so. And so the domain of this was what they asked for. And most people got it right, but I still saw a lot of confusion here. You would start with this endpoint and this endpoint. So let's just say that this was at -2. So starting at -2, and it's a closed circle. So it's less than or equal to my x, which is less than or equal to, no, sorry, less than, because this is an open circle, and let's say that that stopped at 2. So that would be the domain of this section here, and then we would have to write a separate domain for this section because there's that break in my graph right there. So that section right there would be everything greater than open circle, so no equal sign, the 2. So some of these you're going to have 2 separate domains for. So this example here, I've written out the domains. So you start here at -5 on my x-axis, and it's going to go to -1 and closed circle. So equal bar with this inequality, no equal bar with this one at -1. And then I have to stop because there's that break in the graph. So I'm going to pick up again and say, okay, from -1, but not including, to 6, there's another section of line. So continuous from -5 to -1, break, continuous from -1 to 6, and not discrete, because it's connected here. And then the range, though, my lowest point is a -5, closed circle. My highest point is on the graph here at 5, which would also be closed circle because there's a graph there. So these points don't matter because that point is filled in elsewhere on the graph here. So I think that's probably the most difficult kind of domain and range you'll see. Another big thing is right here. Know the difference. I still see confusion right here. If it's connected at all, I don't care how short the line, and if your line is just like this, it's connected, it's continuous. Only from here to here, but it's continuous. The only time it's discrete is if you have separate dots that are not connected, and even if they are in a line like this, if they're not connected, when they give you the picture, they give you the example, then it's discrete, not continuous. But if it has any line on it at all, it's continuous, and then you're writing it with inequalities, whereas discrete, you're writing it as name those points, list the x and y values. Okay, so like I said, I'm attaching quite a number of practice pages to the video. Again, I am not taking a grade on these, they're just to help you, because having tax crammed into the same class with EOC testing has been really difficult, and we don't have the time for extra review days, unfortunately. Make flashcards, so you've got your index cards that we had earlier in the year, and use those to help drill yourself and memorize any of the vocabulary, and also to memorize your parent functions. Any questions you have over the work, or anything else in this, or just concerns, come talk to me, because I'd be happy to help you with that. And we'll start on category 2 just as quickly as I can.